All right. So we're diving into balance in the aspect ratio of the momentum support of a 2D collisionless plasma today. And going deep into some serious math.
Oh, yeah.
You actually shared this paper with me, so you already know this. But it looks at whether knowing how much a two-dimensional collisionless plasma spreads out, like in one direction, can help us predict its spread in the other direction.
Okay.
Essentially, can we put bounds on the aspect ratio of its momentum support?
Yeah. And what's fascinating is that they actually do establish those bounds. They prove that even if the plasma expands a lot, significantly in one direction, there's a limit to how narrow it can become in the other.
I love it. And I'm excited to unpack all the mathematical machinery that they use to actually achieve this.
Okay.
So let's start at the very foundation. The relativistic Vlasov-Maxwell system, or RVM system as they call it.
Right.
That kind of sets the stage for the whole paper.
Right. Absolutely, yeah. The RVM system, it's laid out in equations 1 through 3. It basically encapsulates the fundamental laws that govern collisionless plasmas.
Okay.
So you have the Vlasov equation, that's equation 1.
Right.
And it describes how particles in the plasma move over time, influenced by electromagnetic forces. You can think of it like a microscopic GPS, tracking each particle's journey.
Oh, I like that.
Yeah.
So it's like their own little roadmap.
Exactly.
And then, of course, those forces themselves are actually generated by the charged particles as described by Maxwell's equations.
Yes.
So it's a beautiful example of like a self-consistent system.
Yes.
The particles create the fields, and the fields are what guide the particles.
Exactly. And a crucial finding from previous research, which this paper builds upon, is that the 2D RVM system is globally well posed. So this means that solutions exist for all time.
Okay.
And they don't exhibit any wild, unphysical behavior. And so this well-posedness was proven by actually demonstrating that the momentum support, which is denoted by the capital omega of t, remains bounded for finite times.
Okay, so their velocities, the particles might be zipping around, but their velocities stay within some finite range.
Exactly, yeah.
Okay, and so to connect this to the paper's kind of central question, the authors really aim to control the shape of this momentum support. Specifically, its aspect ratio, right?
Precisely, yeah. They leverage an important inequality from prior work, it's equation 6, which links the strength of those electromagnetic fields to the size of the momentum support. And the logic is, if you can kind of constrain the fields, then you can constrain the momentum.
Okay.
And ultimately, understand how much the plasma can stretch in different directions.
So it's like a chain reaction of mathematical control leading us toward understanding this shape.
Right. Exactly.
But how do they actually quantify the size of this momentum support in a way that's useful for their goal?
Okay, so they introduced two measures, P2 of t and P of t. They're defined in equations 8 and 10, respectively. P2 of t is fairly straightforward. It measures the maximum momentum in the E2 direction, or what we might think of as the vertical direction.
Okay, so it's capturing how far the momentum support kind of extends vertically.
Exactly.
Okay, so P of t, the combined measure, it seems to be capturing more of the overall spread of the momentum support, kind of incorporating information from both directions.
Yeah, you got it. P of t takes into account both P2 of t, as well as the potential expansion in the, horizontal direction.
Okay.
And the core goal of the paper is to link the growth of P of t to 2 of t. So essentially showing that if P of t increases a lot, meaning the momentum support is, expanding horizontally, P2 of t can't stay too small. Right. In other words, the plasma can't become an infinitely thin line, even if it stretches out, really far in one direction.
That's a really neat way to frame it. So they're saying there's some fundamental limit to how squished that momentum support can get.
Right.
But how do they actually go about proving this?
So one of the key tools they use is this concept of characteristic curves, which is described by equation 13.
Yep.
And these curves allow us to track the trajectory of individual particles in the plasma over time.
So we're drawing the path each particle takes as it's pushed and pulled by these electromagnetic forces.
Exactly. And by analyzing these curves, they can actually relate a particle's initial momentum to the total push that it receives from the electromagnetic fields along its path. So equation 13 basically sets an upper bound on the magnitude of a particle's momentum based on its initial momentum and the integral of the electromagnetic force along its trajectory.
Okay, so by understanding how the electromagnetic forces influence each particle's path, they can control how much that overall momentum support can expand.
Right, exactly.
It makes sense. But then, looking ahead, the math starts to get pretty intense. They break down the electromagnetic force, denoted by K, into several components, right? KT, KS1, and KS2.
Yeah.
And bounding each of these seems to be crucial for their proof.
You're absolutely right. Each of these components represents a different aspect of how the electromagnetic fields interact with the particles. And controlling each one is essential for establishing that overall bound on the momentum supports growth. So let's take a closer look at how they handle KT, which is defined by equation 15.
All right, so KT involves this integral that seems to be considering like the entire history of the plasma, right?
Yeah.
From its initial state at S0 all the way up to the current time, ST.
Right.
And it's like taking into account how that particle density function, S, has changed over time and how that contributes to the electromagnetic force at this particular point, X.
That's a great observation. It really highlights the non-local nature of the electromagnetic interaction. To tackle this integral, the authors employ a very clever change of variables. So they shift the focus from the absolute position of the particles, which is Y, to their relative position with respect to the point of interest, X. So they introduce the dimensionless variable, and that's equal to Y minus X, divided by T minus S.
So instead of asking where are the particles, we're asking where did they come from relative to X.
Exactly, precisely. And this transformation actually allows them to simplify the integral considerably. And to further simplify it, they actually rotate the coordinate system so that the momentum vector P is always aligned with one specific axis. This eliminates the angular dependence and allows them to directly calculate the integral over Schiss. And this really clever manipulation leads to a bound for KT presented in equation 22 that depends on T and P2 of T.
I see. So by changing variables, strategically rotating the coordinate system, they managed to tame this seemingly really complex integral and extract a bound that depends on the quantities they're interested in controlling.
Exactly. They utilize powerful mathematical tools to break down a complicated problem into manageable pieces. But as you mentioned, the real challenge lies in bounding those other components of the electromagnetic force, KS1 and KS2.
Right. And just glancing at equations 16 and 17, they look even more daunting.
Yeah.
KS1 involves the electromagnetic force K itself inside the integral.
Yes.
Creating this kind of feedback loop.
Exactly.
And then KS2 introduces this new quantity, K, which seems to be related to the energy density of the electromagnetic fields.
You're getting right to the heart of the matter.
Okay.
These terms represent the intricate interplay between the particles and the fields that they generate.
Right.
And bounding them requires, even more sophisticated techniques and a deep understanding of the underlying physics. So are you ready to dive into those details?
Absolutely. I'm eager to see how they unravel these complexities.
Yeah.
Let's start with KS1 and that feedback loop that you mentioned. How do they even begin to approach that?
So to tackle KS1, the authors use this clever strategy involving the concept of a light cone emanating from the point X, where we're trying to bound the electromagnetic force.
Right. And just to clarify for our listeners, this light cone, it represents the region of space-time that can causally influence the electromagnetic force at X.
Exactly.
Essentially, anything outside this cone can't affect what's happening at X.
Yes.
Because information can't travel faster than light.
Precisely. And the authors, they actually divide the integral for KS1 into 3 regions, each representing a different part of this light cone. This lets them analyze how the electromagnetic force, K, contributes to the integral in each region, taking into account the constraints imposed by causality.
So it's like they're dissecting the integral piece by piece.
Yeah.
Based on how information propagates through the plasma.
Exactly. Yeah.
That's a really neat approach. And I'm guessing this careful analysis allows them to derive a bound for KS1.
Exactly. By leveraging conservation laws and a powerful inequality known as Holder's inequality, they actually obtain a bound that depends on T, the square root of log T, P2 of T, and also a measure of the maximum strength of the electromagnetic force up to time T. This bound is presented in equation 25.
I see. So even though KS1 involves that tricky feedback loop where the force depends on its past values, they've managed to establish this bound by carefully considering the causal structure of the problem.
Right.
Applying those appropriate mathematical tools. Very impressive. But now we're faced with KS2, which from the looks of equation 17, seems even more intricate. It involves this Ke term that we haven't really talked about yet.
You're right. KS2 is arguably the most challenging term to bound.
Right.
K, which is defined in equation 18, represents the energy density of the electromagnetic fields, and it actually plays a really crucial role in this part of the proof.
Okay.
And what's remarkable is that K satisfies a conservation law, also shown in equation 18. And this conservation law states that the total amount of Kg within a specific region of spacetime, called the backward null cone, emanating from X, actually remains bounded over time.
Okay, so it's like having this fixed energy budget within this backward null cone.
Exactly.
And this cone, just to clarify for our listeners, represents the region of spacetime that can causally influence events leading up to the point X.
Precisely. And the authors, they ingeniously leverage this energy budget to control the growth of KS2. To do so, they introduce a new quantity, Ks, which is defined in equation 27, and it captures how the particle density function is distributed with respect to direction and momentum. They then rewrite the integral for Ks2 in terms of Ss and K, allowing them to exploit that conservation law.
That's a brilliant strategy. By reframing the problem in terms of this conserved quantity, Ksg.
Right.
They found a way to constrain the growth of KS2.
Yeah.
But phase S itself looks pretty complicated. How do they handle that?
So this is where the author's mathematical prowess really shines. They meticulously analyze the singularities in the integrand of Sathas using polar coordinates and a clever decomposition based on angles.
Okay.
By carefully bounding SAS in different regions of momentum space, they ultimately obtain a bound for KS2, which is presented in equation 58.
Wow, that's quite a feat. They really had to navigate a mathematical maze to extract that bound, and I'm guessing the details of that derivation are probably beyond the scope of our conversation today.
You're right. Yeah, the full derivation involves a lot of intricate steps and subtle arguments.
Yeah.
But the key takeaway is that they managed to control the growth of KS2 by carefully leveraging that conservation law for Kate and meticulously analyzing the behavior of SAS.
Okay, I'll trust you on the details there.
All right.
So we've now discussed how they bounded each component of that electromagnetic force, KKT, KS1, and KS2.
Yes.
What happens next? How do they actually use these individual bounds to prove their main result?
So now it's time to put all the pieces together. Okay. Remember, equation 14, which relates the growth of P of T to the total electromagnetic force, K.
Yes.
They plug in the bounds that they derive for each component of K.
Okay.
And this results in an inequality that controls how fast P of T can grow.
It's like they analyzed each ingredient separately.
Yeah.
Now they're combining them to create the final dish.
Precisely. To further refine this inequality and isolate P of T, they utilize another powerful tool, Young's inequality.
Okay.
And this inequality allows them to strategically rearrange terms and introduce a small parameter that helps to control the overall growth of P of T.
Okay, so Young's inequality acts like this mathematical lever, giving them the control they need to manipulate that equation.
Right.
Extract that desired bound. And what is the final outcome of all this mathematical wizardry?
So the grand finale is equation 61, a bound on P of T expressed solely in terms of P2 of T. And this inequality demonstrates conclusively that the aspect ratio of the momentum support cannot become arbitrarily large. Even if the plasma expands a lot in one direction, there's a fundamental limit to how narrow it can get in the other.
That's a remarkable achievement. They've successfully proven that there's this inherent constraint on how much a 2D collisionless plasma can stretch out. And this constraint arises directly from those underlying laws of physics. Encoded in that Vlasov-Maxwell system.
Exactly.
But there's one subtle detail in equation 61 that we shouldn't overlook. That logarithmic term.
Right.
It might seem minor, but it actually plays a significant role in that final result.
Yes.
I mean, without that logarithmic term, that bound would be much tighter, implying a stricter limitation on the plasma's expansion. What's the significance of its presence?
So the logarithm introduces this degree of flexibility, allowing for more potential expansion in one direction, even as the plasma grows in the other. So it essentially softens that constraint imposed by the other terms.
So it's like the logarithm is giving the plasma a bit of wiggle room.
Exactly.
A little bit more freedom to move around.
Precisely. But to arrive at their clean final result, stated in Theorem 1.
Okay.
The authors actually have to carefully handle this logarithmic term, and they demonstrate that even though it grows with time, it doesn't grow too quickly to spoil the overall constraint on that aspect ratio.
Okay, so it's a bit of a wild card, but they've managed to keep it in check.
Exactly. Now, with all the pieces in place, let's just take a moment to appreciate the elegance and power of the author's argument. They've combined physical insights with sophisticated mathematical techniques to establish a fundamental constraint on the behavior of 2D collisionless plasmas.
It's truly impressive. They started with this, seemingly simple question about the shape of that momentum support.
Right.
And ended up weaving this tapestry of intricate mathematics, conservation laws, these deep physical principles to arrive at their answer. But I'm curious, what's the broader significance of this result? How does it impact our understanding of these plasmas and their applications? This paper has certainly been a mathematical deep dive. But I think what excites me most is that it's not just about solving a specific problem. It's about opening these new doors for understanding these complex systems.
Yeah, I completely agree. The techniques they've developed here, I mean, they have broader implications beyond just this, specific question of aspect ratio bounds. For instance, you could apply them to studying plasma instabilities, which is, a very critical area in plasma physics research.
Oh, that's a fascinating thought. Instabilities, those are those pesky disruptions that can throw a plasma's behavior completely off kilter, right?
Exactly.
If we could use these techniques to analyze how instabilities develop and propagate, that would be a major breakthrough.
Yeah, imagine if we could actually identify early warning signs of an instability.
Right.
Maybe based on subtle changes in the momentum support or other, related quantities.
Yeah.
That would be transformative for fields like fusion energy research, where controlling plasma stability is paramount.
Right. If we could anticipate and mitigate instabilities in a fusion reactor, it could significantly accelerate our progress toward clean energy.
Exactly.
It's amazing how a theoretical result like this could have such a tangible impact on one of the biggest challenges facing humanity.
Absolutely. It really underscores the importance of fundamental research and how seemingly abstract mathematical explorations can actually pave the way for practical breakthroughs. But while we're talking about broader implications, there's one question we can't ignore.
What about 3 dimensions?
The elephant in the room?
We've been talking about these 2D plasmas.
Right.
But the real world, of course, is 3D. And you mentioned earlier that analyzing the Vlasov-Maxwell system in 3 dimensions is significantly more challenging.
Right.
What makes it so much harder?
Well, think about it, geometrically. In 2 dimensions, we're dealing with shapes in a plane. Circles, rectangles, things like that.
Okay.
But in 3 dimensions, you have spheres, cylinders, cones, all sorts of complex shapes that can interact in far more intricate ways.
It's like going from drawing stick figures to sculpting a full-blown Renaissance masterpiece.
Precisely. And that added geometric complexity, it translates into mathematical complexity.
Right.
The equations themselves become more intricate.
Yeah.
And the tools needed to analyze them, they become more sophisticated.
So it's not just that we haven't found the answer yet.
Right.
It's that we might need completely new mathematical frameworks to even approach the problem in 3D.
That's right. The 3D Vlasov-Maxwell system, it's a vast uncharted territory. It's a fertile ground for future research.
Okay.
Whether similar bounds on the momentum supports aspect ratio exist in 3 dimensions is still, an open question.
It is.
It's entirely possible that the added dimension introduces fundamental changes to the plasma's behavior.
It's both exciting and humbling to realize how much we still don't know. It seems like every answer in plasma physics leads to even more intriguing questions.
That's the beauty of scientific exploration.
It is.
And this paper, despite focusing on this seemingly, niche topic of 2D collisionless plasmas, has provided us with valuable insights and tools that could illuminate our understanding of these systems in a broader context.
I couldn't agree more. It's been a thrilling journey through intricate mathematics, challenging concepts, and these tantalizing mysteries that still lie ahead.
Well, I hope our listeners have enjoyed this deep dive as much as we have. It's been a privilege to delve into this fascinating research and explore its implications.
Absolutely. And who knows, maybe someone listening right now will be inspired to pick up the torch and tackle those unsolved mysteries in 3D plasma physics.
Right.
Until then, keep exploring, keep asking those questions, and keep diving deep into the wonders of the universe. All right, let's jump into another deep dive. This time, you sent over this research paper, Bounds on the Aspect Ratio of the Momentum Support of a 2D Collisionless Plasma. And you're really interested in the math behind it, especially the proofs.
Yeah,
so
absolutely.
Get ready for equations.
Okay.
So before we get into that, I mean, this whole idea of bounding the aspect ratio to predict long-term behavior of plasmas.
Right.
It's pretty wild.
It is. It's I mean, it's really interesting work because it's almost like trying to predict, like a landscape as it changes over time, but instead of a physical landscape, it's this momentum.
Yeah. It's like a momentum landscape.
Yeah.
So let's back up for a second.
Okay.
We're dealing with collisionless plasmas here.
Right.
Meaning the particles mainly interact through electromagnetic forces, not like direct collision. So what's the typical mathematical framework for modeling that kind of system?
So we would use the relativistic Vlasov-Maxwell system.
Okay.
Or RVM.
Okay.
And this is a system of coupled equations, the Vlasov equation and Maxwell's equation.
Okay, cool.
Yeah.
So let's start with that Vlasov equation. What's it telling us?
So the Vlasov equation essentially describes the evolution of the particle density function over time. And in 2 dimensions, this equation looks like this.
Okay.
Partial BIC, F plus F. F plus E, B plus F plus E plus F.
Wow, okay.
Yeah.
So F is the particle density function.
Yeah.
T is time x is position, P is momentum. E and B are the electric and magnetic field.
Right.
And P hat is the unit vector in the direction of P.
Yes.
And P hat perp is perpendicular to P.
Yeah, exactly.
Okay.
So you can see how
So we can see how the particle density function is changing over time, position and momentum. And those are all influenced by the electric and magnetic field.
Exactly. And that's really what the Vlasov equation is describing.
Okay.
Is that evolution.
We're talking about collisionless.
Right.
Right. So where do those fields come into play?
Right. So that's where Maxwell's equations come in.
Okay.
So they describe how the electric and magnetic fields themselves change over time and space due to the charged particles.
Okay. So it's this
it's this coupled system.
Beautiful interplay between the two.
Right.
The particles affect the fields and the fields affect the particles.
Exactly. And that's what makes it really hard to actually solve.
Yeah. So now this paper is really focused on this concept of bounding the aspect ratio of the momentum support. What does that even mean?
So the momentum support is denoted by omega, and that's essentially the region in momentum space that all the particles occupy at a given time.
Okay.
And the aspect ratio really describes the shape of this region.
Okay.
Like how stretched out it is in one direction versus the other.
Gotcha.
And one of the reasons this is so important is if this were to become unbounded, mathematically we would run into these singularities.
Yeah.
And the problem would become very, very hard to solve.
Singularities, those are.
Yeah. And I mean, this is really one of the big open problems, even in 3 dimensions.
Right.
For this system of equations.
So really it's about trying to contain the shape to make sure it doesn't blow up.
Exactly. So they define P2T as the maximum momentum in one direction.
Okay.
Specifically the E2 direction.
Okay.
And then they define PT as the maximum momentum in the orthogonal direction.
Okay.
Plus a term related to P2.
Gotcha.
And they're trying to bound PT in terms of P2T.
Okay. So it's like we're putting these mathematical constraints on how stretched out it can get.
Like guardrails almost.
Yeah, exactly. Yeah.
Yeah.
So where do they begin with this?
So they start with this concept of characteristic curves.
Okay.
So imagine you're tracking a single particle in this plasma. The characteristic curve is essentially like a mathematical description of that particle's trajectory.
Gotcha. So we're like plotting its...
Exactly. Plotting its position and momentum.
And
seeing how it's momentum.
And you can see how it's influenced by these electromagnetic forces as it travels.
Exactly.
And so what's really cool about these characteristic curves is they link the particle's momentum at any given time to its initial state and the cumulative electromagnetic force it's experienced along that path.
Yeah.
And this is actually given by equation 13, which is KSXP plus M by S XPS path or pay-go.
Okay, so break that down for me.
So PP is the momentum of the particle at time t.
P0 is its initial momentum.
Gotcha.
And KSSPES represents the electromagnetic force at time S along the trajectory, which is represented by Xs.
Okay, so we're basically like rewinding the particle's journey to see how the forces have shaped its momentum.
Exactly. And so from this equation, they derive equation 14, which is PAC0 plus INSEAS XCY SSP0 plus INSEAS X's SPS.
Whoa, okay.
Yeah.
So what is that telling us?
So this is really the basis of their proof.
Okay.
And it links PSC, that maximum momentum in one direction, to PTT, the maximum momentum in the orthogonal direction, and then to this integral of the electromagnetic force along those characteristic curves.
Okay, so this is like our roadmap.
Exactly. It's a roadmap to bound that aspect ratio.
Gotcha.
But we have this integral of K, and K is a very complicated expression, so that's what we have to deal with next.
Well, so before we even get to that, we've got to
taught to deal with K.
Understand K.
Right.
So the electromagnetic force K is a pretty complex beast. So they break it down into these more manageable pieces, KT, KS1, and KS2. And each one kind of represents a different aspect of how these electromagnetic forces are influencing things.
So let's break down those components.
All right.
What is KT all about?
Okay, so KT is really the contribution to the force that comes directly from the distribution of the particles themselves.
So like the particles themselves are creating.
Exactly how the particles themselves are creating and shaping the electromagnetic fields.
So the more particles you have packed together, the stronger their influence.
Yeah, that's a good way to think about it.
Okay.
And then KS1 represents kind of the contribution from the electromagnetic field itself. Like its internal dynamics. It's got its own energy momentum separate from the particles. Gotcha. Okay, what about that last one, KS2?
Yeah, so KS2 is a bit tricky. It involves this special quantity, kg, which depends on both E and B, the electric and magnetic fields.
What's so special about K?
So the nice thing about K is it actually obeys this very useful conservation law, which is given by equation 18, partial K plus operator name type right.
Okay, so what are we seeing there?
So V hat is just the velocity of the particle. And P naught is this quantity that depends on the momentum. And so this conservation law, along with the conservation of mass, which is equation 20, and the conservation of total energy, which is 21, are all going to be really useful in helping us bound KS2.
Conservation laws, those are.
Yeah, they're very helpful because, you know, that certain quantities remain constant. And that really helps simplify.
Yeah, it simplifies the problem. So we've got these three components broken down. What's the next step?
So now they need to actually prove bounds on each of these components. KT, KS1, and KS2.
So like a mathematical quest.
Exactly. And they do this through a series of propositions.
Okay, cool. So which one do they tackle first?
So they start with proposition 4, which bounds KT. And this actually uses a lot of clever techniques. They do a change of variables. They rotate the coordinate system.
Ooh, a coordinate rotation.
Yeah.
Basically, they transform this integral from over a disk to an integral over a unit ball. And then they rotate the coordinate system so that the unit vector p hat is aligned with one of the axes.
Gotcha. So they're really...
And it really simplifies the calculation.
Using the geometry.
Yeah, exactly.
To make the math easier. And so they get a bound on KT that depends on time, T, P2T, and PT.
1 down, 2 to go. What about KS1?
Yeah, so KS1 is a little bit more intricate. They actually have to divide the light cone emanating from a point, Tx, into 3 different regions.
And the light cone is?
Yeah, so the light cone represents all possible paths a particle could take.
Gotcha.
From that point.
Okay, so we're looking at all the
possible trajectories. And the reason they have to divide it into 3 regions is because the behavior of KS1 is different in these regions.
Okay, so different strategies for each.
Exactly. In the first region, they actually use the conservation of total energy and a bound they derived earlier.
Okay, so they're building on.
Yeah, they're building on what they've already done.
And then
in the second region... they use this really powerful tool from analysis called Holder's inequality.
Holder's inequality.
Yeah, and it's basically a way to kind of control the size of integrals by shifting weight between different parts of the integral. So it's like a
very useful tool.
Mathematical Swiss Army knife.
Exactly.
Useful in lots of situations.
Yeah.
What about that third region?
So the third region is kind of similar to the second. They use Holder's inequality again.
Okay.
And they get a bound on KS1.
So they've really meticulously gone through.
Yeah, they've systematically gone through
each one of those slices.
Yeah, to bound KS1.
So 2 down, 1 to go.
Yes.
And the last one's the trickiest.
Yes, the last one, KS2, is definitely the most challenging. And this is where this quantity K-Koji really comes into play.
Okay.
And the function that they use to analyze KS2 can actually become singular. Under certain conditions.
Okay.
Which leads to some...
All right, so we're going to have to, we'll have to dive into that.
Dive into that.
A little more next time.
Next time.
So welcome back to our deep dive into bounding that aspect ratio of the momentum support. Last time we left off, we had successfully bounded KT and KS1, those two components of K. Now it's time to look at that trickiest part, KS2.
Right, and KS2 is the one that involves that special quantity KT.
Exactly, and if you recall, KT is the one that depends on both the electric and magnetic fields and obeys a conservation law, right?
Yeah, so how does that play into bounding KS2?
Okay, well, to analyze KS2, they introduce a new function, Hess.
Okay.
And it's defined like this sigma xp1 plus Hess t1 plus Hess ft1.
Okay, so we're integrating over momentum space.
Right.
But with this weighting factor.
Exactly. So Hess is defined as AS, TS.
Okay.
And V hat is P hat over P naught.
Oh,
and so the problem with KS2 is that this S function can actually become singular.
Okay, when you say singular, you mean it like...
It blows up to infinity.
It blows up, okay.
Yeah, under certain conditions.
What are those conditions?
So this happens when that denominator in the integrand of Servus approaches 0.
Okay.
So to understand when that happens, they define 2 angles.
Okay.
And those are defined like this: Sera fetus theta and then square fet E1.
Okay, angle. So theta fetus is like the angle?
Is the angle between the momentum vector and the E1 axis.
Okay.
And is the angle...
Between negative...
Between negative S theta...
The E1.
And the E1.
Okay.
And so the problem with that singularity in Sea occurs when both E and the difference between eta theta are very small.
Okay, so we're pinpointing where these singularities occur.
Right, exactly.
Oh, how do they handle that?
So to handle that, they decompose KS2 into several smaller pieces that correspond to different ranges of these angles.
Gotcha.
So first they split KS2 into 2 parts.
Okay.
K does 2 and K hat S2. And these correspond to the range of angles where -2 is less than or equal to, which is less than or equal to 2 for K tilde S2.
Yeah.
And then the other half is K hat S2.
Okay, why split it up like that?
So the singularity in Sesha behaves the same way in both halves.
Okay.
So they can just analyze one of them.
Okay, so just focus on...
Yeah, they focus on K tilde S2.
Okay.
And then they further decompose K tilde S2 into 4 smaller pieces.
Okay.
And those are written like this: KS1, 2, 1, down. 1, KS2, 1, 2, 1, Italis, 2, 2, 1, 2.
Okay, so we're just slicing and dicing this.
Slicing and dicing, yeah, exactly.
Into smaller, more manageable pieces.
Exactly, so that they can carefully analyze for all the different angles.
Yeah, and for each of these pieces, they apply, Cauchy-Schwarz. They apply that conservation law for QK.
Right.
And some other clever trigonometric bounds to derive estimates.
So we're just pulling out, we're using all the tools.
All the tools, all the inequalities.
Exactly.
Right.
And then to further refine their bounds, they introduce 3 time-dependent quantities, Okolam and Ga.
Okay.
And these are defined in terms of P2T and 3 functions, AT, BT, and CT.
Okay.
Which they'll choose later to kind of optimize the bounds.
So it's like an optimization problem.
Exactly. Yeah, it's like a mini optimization problem within the larger problem.
Okay.
And so each of those 4 pieces of K tilde S2 has a bound that depends on A, B, and C.
Okay.
And the final step is to choose those functions, A, B, and C, to minimize
the overall bound.
The overall bound on KS2.
Okay, so what's the final verdict on KS2?
So they find that the optimal choice for C is given by this CT left fire, left 2 PT plus 2 right, left to left 5 plus 1 right.
Oh, wow.
Yeah, and they derive some bounds for A and B as well.
Okay.
And this is all presented in Proposition 6.
Okay, so...
And so with that, they successfully bound KS2.
We bounded the beast.
We bounded the beast, yeah.
All three components.
All three components are done.
Done. Does that mean we're ready for Theorem 1?
Almost. So remember equation 14?
A roadmap.
A roadmap.
To the aspect ratio.
We now have bounds for all the pieces of K,
right.
So we can plug them into that equation.
Okay, so let's put it all together.
Yeah, so when they substitute the bounds from propositions 4, 5, and 6 into equation 14,
yeah,
they get this rather long inequality.
Okay.
Involving PT, P2T, and various terms related to T and log of PT.
But I'm assuming?
Yeah, they can simplify.
It simplifies.
It does. So they use the fact that both KT and P2T are increasing functions of time to bound the L infinity norm of K. Okay. And then they apply Young's inequality.
Young's inequality. Another inequality.
Another inequality.
So useful.
Very useful.
What does that one let us do?
So Young's inequality in this context lets them kind of control the growth of certain terms by like redistributing the exponents.
Okay.
It's a delicate balancing act.
We're tweaking exponents to get what we want.
To get what we want, yeah.
Okay, what do we get?
So after applying Young's inequality and carefully choosing the parameters, W, P, and Q, they actually set W to 13, P to 43, and Q to 4. Okay. They arrive at a much cleaner inequality. Okay. But P to T isn't quite isolated yet. Okay. So to do that, they take the logarithm of both sides.
Logarithm trick.
Yeah. Right. And use the fact that log of x is less than or equal to x to the 6th for sufficiently large x.
Okay, so that lets them...
And that allows them to isolate log on one side. Okay. And get a bound that depends only on the log of TP2.
All right, we're almost there.
Almost there.
We made it.
Yeah, we made it.
Okay, but I think we've got to save Theorem 1.
We'll save the grand finale for next time.
For next time. Welcome back. We've spent the last 2 parts really digging into this proof for bounding the aspect ratio of momentum support. We broke down the electromagnetic force, bounded all the components, and dealt with all those tricky singularities. So now, let's finally unveil the main result. Theorem 1.
Yeah, so after all that intricate work, the statement of Theorem 1 is actually pretty concise. Okay. It says, for any initial data in CC1 left times math dollars for the 2D RVM system, there exists a unique global solution, FE. Moreover, let PT and PTT defined as before, then a Fira C phi PT plus C2 for all TR dollars, where C1 and C2 are constants depending only on $5.
Okay, so in plain English, what does that actually mean?
So basically, it means we've proven that the maximum momentum in one direction, PAT, is bounded by a function of time and the maximum momentum in the other direction, PDT.
That's a pretty powerful statement.
It is, and it gives us a quantitative way to control the shape of that momentum support over time. So it's telling us that even if the plasma expands really rapidly in one direction, the momentum distribution can't get arbitrarily stretched out in the other direction.
So it's like we've established a mathematical speed limit.
Exactly.
Okay, so what are the implications of all this?
Well, it has big implications for understanding the long-term behavior of these collisionless plasmas, at least their 2 dimensions. Okay. By knowing that that aspect ratio stays bounded, it ensures that the solution to the RVM system exists for all times and remains smooth, meaning we can predict the evolution of these plasmas indefinitely, at least theoretically, without running into any of those singularities.
So it's a big step towards solving that problem of global well-posedness.
Exactly.
You mentioned that it's still an open problem in 3 dimensions. Does this 2-dimensional result offer any clues or strategies for tackling the 3D case?
Well, even though this paper focuses specifically on 2 dimensions, a lot of the techniques they've developed here, things like using characteristic curves, the decomposition of the electromagnetic force, and using all those clever inequalities, could potentially be adapted and extended to the 3D case. So it definitely provides a roadmap, at least for future research, and gives us hope that similar bounds might be attainable in 3 dimensions as well.
It's amazing how this really abstract mathematical work can shed light on such complex physical phenomena.
It is, and it's a testament to the power of mathematical reasoning, you know? We can take these abstract tools and use them to really understand and predict the behavior of the physical world.
It's been a fascinating journey. We've learned a lot about the intricate mathematics behind understanding these plasmas. And for those of you who are interested in exploring further, I'd leave you with this question. What are the real-world implications of these bounds, especially for things like fusion energy research or astrophysical modeling?
That's a great question. It really bridges the gap between this theoretical work and its potential impact on some pretty important scientific challenges.
That's all for this deep dive. Until next time. Welcome back for another deep dive. Today we're going to be looking at something pretty cool. Two-dimensional collisionless plasmas.
These are really interesting systems.
They are, yeah. Yeah.
And you know, they're kind of different because the particles are so spread out, right? That they're not really colliding with each other like in a normal gas.
Yeah, it's more like a...
They're interacting mainly through electromagnetic forces.
Yeah, through fields.
So you can think of things like space plasmas as a good example.
Yeah, exactly. And the paper that we're going to be looking at that's kind of guiding us through this is called Bounds on the Aspect Ratio of the Momentum Support of a 2D Collisionless Plasma.
So this is going to be all about how the shape of this momentum distribution evolves over time. And in particular, they're going to be focusing on the aspect ratio.
So like the width in one direction versus the other?
Right.
Okay, cool.
So this actually builds on some known results about the relativistic Vlasov-Maxwell system in 2 dimensions, which are the equations that govern these plasmas. And it's already been proven that this system is globally well posed.
So that means...
Which means...
It doesn't blow up.
It doesn't blow up. The solutions exist for all time, and they stay bounded.
So that's good.
That's good. And this was shown by proving that the momentum support of the particle density function stays bounded.
Okay, so momentum support, that's the region in momentum space where there are particles.
Yeah, you can think of it as, you have this function that describes the density of particles in momentum space. So how many particles have a given momentum?
Right.
The momentum support is the region where that function is non-zero.
Okay.
So it's where the particles actually are.
Like the occupied zone.
Exactly. And so this paper is going to be looking at how that occupied zone changes over time.
Okay.
And in particular, they introduced these 2 functions, P of t and P2 of t, which are going to be really important for tracking the growth of that momentum support.
So tell me about those.
So P2 of t is the maximum momentum a particle can have in the E2 direction at time t.
Gotcha.
So you can think of E2 as like our special direction.
Our reference direction.
Right. And then P of t is a more general upper bound on the momentum, but it's related to P2 of t through a power of 1 over W, where W is some number between 0 and 1.
Okay.
That we'll figure out later.
Interesting.
But the important thing is that both P of t and P2 of t are non-decreasing functions of time.
Right. So as time goes on,
the momentum support can only spread out further.
Right. It's not going to like shrink back down?
It's not going to shrink.
Okay, cool.
So the question is, how does the growth of P of t,
the general one,
this general momentum bound, depend on the growth of P2 of t?
In that E2 direction.
Right, in that spiral direction.
Right.
So that's what we're going to be looking at.
Cool. So how do they go about figuring that out?
Well, they use some pretty cool tools.
Okay.
One of them is the concept of characteristic curves. Have you heard of these before?
I have, but maybe you could explain for the listeners.
Yeah, so you can think of these as paths traced by individual particles in this 6-dimensional space.
6 dimensions.
Yeah, it sounds crazy.
Okay.
But you've got time, you've got the 2-dimensional position of the particle, and you've got its 2-dimensional momentum.
Okay.
So that's 6 dimensions.
Right.
And the particle density function, which tells you how many particles are at a given point in this 6-dimensional space, is actually constant along these characteristic curves.
So if you follow
the path of one particle,
back in time, you can figure out where it came from.
Okay, cool. And what else are they using?
Well, they also use conservation laws in a really clever way.
Right, because those are important in physics.
They are, and they're essential for proving this theorem.
Okay.
And what they're trying to do is bound this momentum support.
Right.
And in order to do that, they need to control the electromagnetic force acting on the particles.
And that force is given by this function they call K.
Oh, fun.
And so they break down K into 3 components, KS1 and KS2.
Okay.
And these represent different ways that the electromagnetic field can affect the particles.
So they're like breaking down this complicated force into
breaking it down.
More manageable chunks.
Exactly.
Okay.
And if you look at the formulas for these components, they involve these integrals over space and time, which basically means that the current electromagnetic force depends on the past positions of the particles and the past values of the field.
Right, so everything that's happened before kind of influences what's happening now.
Exactly.
Okay, that's cool.
So the real challenge is to bound each of these components of K.
Okay, so now we're getting down to the nitty-gritty.
And we're getting into the math.
All right, I'm excited. Okay, so KT, the one related to the past positions, is relatively okay.
Yeah, they're able to bound that one by T times P, 2 of T times the logarithm of P of T. So you can see that it grows with time, but it's also influenced by both of these momentum bounds.
Okay, so the bigger those bounds are,
yeah,
the bigger this term could potentially be.
Right.
Okay, cool. What about KS1? Is that one also straightforward, or is that a little trickier?
That one's a little bit more tricky.
Okay.
It represents the interaction between the electromagnetic force and the particle density.
Okay.
And they actually have to use some clever tricks to bound this one. They split the integral into regions that are within something called the light cone.
Okay, so the light cone, that's like all the points in space-time that could be reached by a light signal.
Right. It's kind of a way of visualizing causality because nothing can travel faster than light.
Right, so if it's outside the light cone,
yeah,
it can't influence what's happening right now.
Exactly.
Okay, cool. And so how does that help them bound this term?
Well, it lets them carefully handle these potential singularities.
So like points where things could blow up to infinity.
Exactly. And then to get a bound, they use something called a Holder exponent.
Oh, yeah.
Which, without getting too technical,
Yeah.
just allows them to have some flexibility in how they control the growth of this term.
Okay.
And so the final bound involves P of T raised to a power that depends on this Holder exponent.
Okay, so it's like
That they can kind of...
they have some control over how steep
Exactly.
that bound is.
Yeah.
Okay, cool. So KT, we've got that one. KS1, we've got that one. What about KS2?
Okay, so this is the big one.
Oh, boy.
This is the most challenging one.
Okay.
And it involves this quantity called sigma sub s.
Okay.
Which basically captures how the particles are distributed in momentum space.
Okay.
And it's defined in a way that can lead to some tricky mathematical situations.
Uh-oh, what kind of tricky situation?
Well, so it's defined as an integral over momentum space, but it has this denominator that can become very small.
Okay.
Which can make the whole expression blow up. So to deal with this, they introduce these three angles, alpha, beta, and gamma.
Okay, angles. What do angles have to do with this?
Well, these angles allow them to divide the integral into different regions.
Okay.
And by choosing these angles carefully, they can control how close that denominator gets to 0.
So they're like taming those potential blow-ups.
Exactly, by dividing and conquering.
Okay, smart. And then what do they do?
So for each of these subregions, they apply the Cauchy-Schwarz inequality.
Oh, yeah, that's a classic.
Yeah, to each sub-integral.
Right.
Which allows them to isolate the contributions from sigma sub s and this other quantity, k sub g.
Which is related to the electric and magnetic fields.
Right.
Okay, so they're separating out those two effects.
Exactly.
Clever. And so then what about the contribution from k sub g? How do they control that?
Well, they have this really clever trick. They use a conservation law.
Right.
That provides a bound on the integral of kg squared over a specific region.
Okay, so those conservation laws are really coming in handy here.
Yeah. They're essential.
Yeah. And what about the estimates for sigma sub s itself? Because I remember seeing a lot of trig functions.
Oh, yeah. Those are pretty involved.
Yeah.
You have to really carefully analyze the geometry of the momentum support.
Okay.
And how these angles, alpha, beta, gamma, define these different regions.
Right.
And so you have to use a lot of trig identities and bounds to simplify those expressions.
Okay.
And understand how sigma sub s behaves in each of these regions.
Gotcha. And I also remember seeing some arctangent functions popping up.
Yeah, so the arctangent function has this nice property that its derivative is bounded.
Right.
And since we're dealing with integrals over angles, this helps to control how much certain terms can vary.
Right, so it's like a smoothing factor.
Exactly.
Okay, cool. So they've got all these different regions. They've got these estimates for sigma sub s. What's the final step?
Well, the final step is to choose those angles, alpha, beta, gamma, optimally.
Right, because those were really important for breaking down that integral.
Yeah, they were essential.
But how do they know what the best values are?
Well, they want to choose the angles that give the tightest possible bound for KS2.
Okay, so it's an optimization problem.
It is.
Okay, cool.
You have to carefully balance the contributions from all these different terms in the bounds.
Okay.
And it turns out that this leads to specific expressions for alpha, beta, and gamma
Okay.
in terms of P of t and in P2 of t.
Okay.
And then you plug those optimal values back into the bound for Ks2.
Okay.
And you get this final bound.
Okay.
Which is t times P2 of t to the power of 3/4 times P of t to the power of 3/4 times the logarithm of P of t to the power of 3/4.
Wow, that's a mouthful.
It is.
Okay, so they've got all three components of K bounded now.
Now we have all the pieces.
Okay, what do they do with them?
Now we put them together.
Okay.
And we use those bounds to derive the main result.
Okay.
And that main result is this inequality that relates P of t.
Right, our general momentum bound.
To the initial conditions and the integral of K.
Right, and that came from those characteristic curves.
Exactly.
Right.
So now we take all these bounds that we worked so hard to find.
For KT and all of that.
For all the components of K.
Right.
And we plug them into that inequality.
Okay, so now we're substituting in those expressions.
Yeah, and it gets a little messy.
I bet it does.
But we can use Young's inequality to help us simplify things.
Okay, Young's inequality, what's that?
So it's a really useful tool for manipulating inequalities that involve products of terms.
Okay.
And it basically lets you redistribute the weight between those terms.
Okay, so like rearrange them and adjust their powers.
Exactly. And so by carefully choosing those powers, based on the structure of those bounds that we found,
right,
we can isolate P of t on one side of the inequality.
So we get P of t by itself.
Exactly.
And that gives us the main result.
That's the main result. And after all that work,
all that math,
we get this beautiful bound,
okay,
which says that for sufficiently large times, P of t is bounded by a constant times t to the 8th power times P2 of t cubed times the logarithm of t times P2 of t all cubed.
Wow, that's a lot of exponents.
It is, but it really captures how the growth of that general momentum bound is constrained by the growth in that E2 direction.
It's amazing how everything comes together.
It is a beautiful result.
We started by defining the problem. We looked at the Vlasov-Maxwell equations.
Right.
We introduced characteristic curves, conservation laws.
That's the good stuff.
And then we broke down that electromagnetic force into all of its components.
Into those three key pieces.
And each step kind of built on the previous one.
Yeah, it was a journey.
Until we got to this amazing result.
A beautiful result.
It's really cool. And it shows that this momentum support.
Yeah.
It can grow.
It can spread out.
But it's not just growing willy-nilly.
Right.
There are rules.
It's not arbitrary.
Yeah, it's following these very specific mathematical relationships.
Exactly. And those relationships are encoded in the structure of those equations.
Right, the Vlasov-Maxwell equation.
And this paper has really illuminated one of those key relationships.
This has been an amazing deep dive.
It has.
But like with any good research, I feel like it's just the beginning.
Yeah, it opens up so many more questions.
Right, like what are the long-term implications of this bound?
What happens to the electric and magnetic fields?
Yeah.
Does it lead to any interesting patterns or structures forming?
Right, and we were just looking at 2 dimensions here.
Right, what happens in 3 dimensions?
Yeah, does it get even crazier?
Does it get even more complicated?
I don't know.
We need more research.
Yeah, this paper has given us a great foundation.
It has.
But there's so much more to explore.
A whole universe of unanswered questions.
Well, this has been a fantastic journey.
It has been a pleasure.
Into the world of collisionless plasmas.
Indeed.
Thanks for joining me.
It was my pleasure.
And thank you to all of our listeners for taking this deep dive with us.
Until next time.
Keep exploring. Welcome to another deep dive, everyone. Today we're going to be tackling some pretty intense math.
Oh, yeah. Definitely getting into the weeds today.
It's all about collisionless plasmas in 2 dimensions.
Buckle up.
We're going to be looking at a paper called Bounds on the Aspect Ratio of the Momentum Support of a 2D Collisionless Plasma.
It's a mouthful, I know.
But it's a fascinating look at how researchers are trying to predict the long-term behavior of these plasmas. And the math they use is pretty mind-blowing.
Yeah, it gets pretty deep. But that's what we're here for, right? To really dissect these complex ideas.
Absolutely. So to set the stage, let's talk about the relativistic Vlasov-Maxwell system, or RVM for short.
Right. So the RVM system is like our foundation here. It's the mathematical model that describes these plasmas where the particles are moving super fast, like close to the speed of light, relativistic speeds.
And it captures how they interact through electromagnetic forces, but without like directly colliding with each other.
Exactly. No bumping into each other in this scenario.
Now, the paper starts by introducing a few key players. We have this function f.
F is all about the density of the particles in the plasma.
Right. And it depends on time, position,
Yes.
and the momentum of the particles.
Since we're in a two-dimensional world here, both the position and momentum are vectors, with two components each.
Yeah, got to keep track of both those dimensions. Now, the researchers use what they call normalized momentum.
Yeah, they denote it with p hat. Basically, they're dividing the momentum by a factor that's related to the speed of light.
It's like a way to keep the math a bit more manageable. When you're dealing with relativity, things can get pretty wild.
Oh, for sure. Simplifying where you can is key.
Then we've got the charge density, represented by Garas, and the current density, represented by J.
These are important because they tell us how the electric charge and current are distributed within the plasma.
So, like, if you know where the particles are and how they're moving,
Yeah.
you can figure out the charge and current they're carrying.
It's all interconnected, like a beautiful, chaotic dance.
And, of course, we can't forget about the electric and magnetic fields, E and B.
They're the forces driving the whole show, making things happen.
Now, in this two-dimensional scenario, the magnetic field, B, is actually represented by a single scalar function.
Yeah, because it's acting perpendicular to the plane of the plasma, so we can simplify it a bit.
Right. So we've got our particle density, our charge and current densities, and the electric and magnetic fields, all interacting with each other, and the RVM system links them all together.
Through a set of equations that describe how they change over time, how they evolve.
The first equation in this system is the Vlasov equation,
Which tells us how the particle density, that F we talked about, changes over time.
due to the movement of the particles and the forces acting on them.
Right. And that force is the electromagnetic force, denoted by K.
It's a combination of the electric and magnetic fields, and it determines how the particles are going to move.
Pushing and pulling them around.
Now, the paper introduces this really important concept called momentum support, denoted by AT.
Think of it like the range of velocities that the particles can have at any given time.
So it's kind of like defining the boundaries of the plasma's behavior in terms of, like, particle speeds.
Exactly. It's like, what's the speed limit for these particles in this plasma?
And a key question that the researchers are trying to answer is, how does this momentum support change over time? How does it shape, like, evolve?
That's where the concept of aspect ratio comes in.
Okay, aspect ratio. So what exactly does that mean in this context?
So the aspect ratio of the momentum support is basically the ratio of its size in one direction to its size in the perpendicular direction.
So, like, how much it's stretched or squished.
Exactly. You got it.
So the paper is investigating whether there's a relationship between the maximum momentum a particle can have in one direction, denoted by P2T, and how large the momentum can get in the other direction.
Yeah, trying to find a link between those maximum momentum, which would tell us a lot about how the plasma behaves over time.
Makes sense. So to tackle this, they introduced this function, PT.
PT is like an upper bound on the momentum support in one direction.
Okay. And how does that relate to P2T, the maximum momentum in the other direction?
Well, they define the relationship between PT and P2T in a way that ensures that PT grows faster than P2T.
So it's like setting up a framework for their analysis, ensuring they're capturing the potential growth of the momentum support.
Yeah, it's like setting the stage for the mathematical fireworks to come.
Now, to make things even more interesting, they break down the electromagnetic force, K, into three components.
KT, KS1, and KS2.
Right, like dissecting this complex force into smaller, more manageable pieces.
Exactly. Each component represents a different way that the electromagnetic field can influence the movement of the particles.
So the challenge then becomes to find bounds for each of these components.
And that's where the math gets really, really interesting.
It sounds like they're diving into a world of integrals, inequalities, and some pretty clever changes of variables.
Oh yeah, they're pulling out all the stops to understand how these forces can influence that aspect ratio of the momentum support. It's pretty impressive.
And what are some of the tools they use to do this analysis?
Well, they use some heavy hitters from analysis, like Holder's inequality and Young's inequality for products. These are really useful for manipulating and simplifying those complex expressions.
So by carefully analyzing each of these force components, they're essentially building up a picture of how the momentum support can change over time.
Exactly. And you know what's really interesting?
What's that?
They found that the most singular regions of the momentum support.
Singular.
Yeah, the regions where the particle distribution behaves kind of in the most extreme way. Those regions are near what we call the E1 direction.
Like the x-axis.
Exactly. And when certain angles involved are like super small.
So it's like finding the hot spots in the plasma where things are really dynamic.
That's a good way to put it.
And all of this leads to their main conclusion, right?
Yeah, they prove that for large enough times, the momentum support in one direction, that's PT, remember? It's bounded by a function of time, the maximum momentum in the other direction, P2T, and a logarithmic term.
So they found a mathematical relationship that tells us how the shape of that momentum support evolves over time.
That's exactly it. It's pretty groundbreaking stuff, and it sets the stage for understanding the long-term dynamics of these 2D collisionless plasmas. But there's still so much more to unpack.
Let's do it. Let's take a closer look at how they tackled each of those force components, KT, KS1, and KS2, because that's where the real mathematical magic happens.
Yeah, that's where the fun begins. Ready to dive into the details?
Absolutely. Let's do it.
Okay, so let's get into the nitty-gritty. How did they actually handle each of these force components? KT, KS1, and KS2. Remember, they broke down the electromagnetic force K into these three parts to kind of simplify their analysis.
Right. It's like a divide and conquer strategy
Yeah.
to understand how this complex electromagnetic field is actually influencing those particles.
Exactly. So first up, KT. They started with a pretty clever change of variables.
Ooh, change of variables. Always fun.
Right. They replaced the spatial variable, y, with a new variable of. That's psi I, by the way, defined as yx divided by ts.
Okay, so what does that actually do? What's the point of that?
Well, this shift, it kind of moves the focus from the absolute position of the particles to their relative position within what we call the light cone.
The light cone. So it's like instead of looking at individual dancers on a dance floor, we're now observing like the patterns they create as they move in relation to each other.
Yeah.
In the speed of light.
That's a great analogy. So this change of variables, along with the fact that the particle density function f is bounded, it allows them to simplify the expression for KT significantly.
Ah, okay. So it's all about making the math a little bit easier to work with.
Exactly. And then they rotated the coordinate system for the integration variable so that the normalized momentum, p hat, always points in the one direction.
So they're like strategically aligning their coordinate system to make the math more manageable.
Exactly. It's like finding the perfect angle to capture the essence of a scene if you were like a photographer.
I like that. So this rotation, what does it actually lead to?
It leads to an integral that they can actually solve directly.
Oh, nice.
Which gives them a bound on KT in terms of time, t, and that maximum momentum in the second direction, p2t, multiplied by a logarithmic term.
Okay, so they've tamed KT. What about KS1? Did they use a similar approach?
Well, KS1 was a bit trickier.
Ah, of course it was.
To handle this component, they divided the integration region into three parts, each representing a different region within that light cone we talked about.
So each section needed its own special attention.
Yeah, each one needed a slightly different approach.
Like they're adapting their tools to the unique characteristics of each region. So how did they tackle the first region?
In the first region, they used the conservation of energy law and the bounds they had already established on the integral of the particle density function.
Ah, so they're leveraging those fundamental laws of physics and the information they've already gathered to make progress.
Precisely. And that led them to a bound for this portion of KS1.
Okay, makes sense. What about the second region?
For the second region, they brought in Holder's inequality.
Holder's inequality.
Yeah, it's a really powerful tool from analysis. It allows you to split the integral into two parts and control each part separately.
So it's like breaking down a complex dance move into smaller steps.
Yeah, good analogy. And then they simplified their calculations further by using interpolation.
Interpolation.
Yeah, it's a way to kind of estimate a function's value between known points.
Oh.
And then in the third region, they used a similar approach as in the second, again employing Holder's inequality and interpolation to obtain a bound.
Okay, so lots of careful analysis and clever techniques going on here.
It's a delicate dance.
And by meticulously combining those bounds from all three regions,
they finally arrived at their estimate for KS1.
And I'm assuming that estimate involves a whole bunch of terms, right?
Oh, yeah. It includes time, t, the square root of the logarithm of time.
Okay.
The maximum momentum in the second direction, P2T, a logarithmic term, and a term involving what we call the supremum norm of the electromagnetic force, K.
Wow, that's a mouthful.
It is, but each term has its own significance.
So they've conquered KT, they've conquered KS1. Now for the final boss, KS2.
Ah, yes, KS2. This one required even more finesse. They started by introducing a new function, that's sigma s.
Okay, and what does sigma s represent?
It basically encapsulates the integral of the particle density function over momentum space, weighted by a factor involving the normalized momentum and a direction vector.
So it's kind of like looking at the overall flow of the dance, how the collective movements of all the dancers create the energy and dynamism of the performance.
Yeah, I like that. It's about understanding the collective behavior of the particles and how their velocities influence that electromagnetic force.
So how does sigma s fit into the picture with KS2?
Well, KS2 is expressed as an integral of this new function, sus, multiplied by another term, K, which represents a specific combination of the electric and magnetic fields. But the tricky part is...
What's the tricky part?
The integration is performed over a light cone.
Integrating over a light cone. That sounds challenging.
Oh, it is. It's like considering all the possible paths that light could take within a certain time interval.
So how did they handle that?
Well, they used a transformation that allowed them to view the integration over the light cone as a series of integrals over what we call conic shells.
So they're breaking down this complex integration into smaller, more manageable pieces.
Precisely. Peeling back the layers of the onion, so to speak.
And I'm guessing there were some additional challenges along the way.
Oh, yeah. A major challenge with KS2 arises from potential singularities in the function S, points where the mathematical expressions could, like, explode, become undefined.
Ah, singularities. Those are always fun.
To address this, they introduced two angles, though. That's theta and phi, which represent the angles between the momentum vector and the E1 direction, and between the negative of the direction vector up and the E1 direction, respectively.
So they're bringing in trigonometry to analyze the geometry of the problem.
Exactly. These angles are crucial for understanding what happens when the denominator of success approaches 0, which is where those singularities might pop up. To navigate these tricky regions, they divided the integral for KS2 into several parts, each defined by specific ranges for the angles day and phi.
So even more dividing and conquering.
It's all about breaking down the problem into pieces you can actually work with. And then they meticulously analyzed each of these parts, using a combination of trigonometric identities, inequalities, and some really clever estimations.
It sounds like a real tour de force of mathematical manipulation.
It was, but they managed to get it done. They arrived at a bound for KS2, which, like the others, involves time, t, maximum momenta, and a logarithmic term.
So after all that work, they have bounds for all three components, KT, KS1, and KS2. Now what?
Well, now they can combine them to obtain a final estimate for the total electromagnetic force, K, like putting all the pieces of the puzzle together. And from there, they can plug this estimate into an inequality that relates PT to the integral of K over time. And after some final manipulations and a clever application of Young's inequality, they arrive at their ultimate role, a bound for PT. In terms of time, key, the maximum momentum in the second direction, PTT, and a logarithmic term.
So they finally have a mathematical expression that describes how the shape of that momentum support evolves over time.
Exactly. It's pretty amazing what they were able to accomplish.
It sounds like it. Okay, so they've successfully bounded all three components of the electromagnetic force, KT, KS1, and KS2, and used those results to find a bound for the momentum support, PPT. What happens next?
Well, now they need to connect these bounds to the aspect ratio of the momentum support. Remember that was their main goal from the beginning?
Oh, yeah, the aspect ratio. I can't wait to hear how they do that. All right, so we've seen how they broke down that electromagnetic force into those three components, KT, KS1, and KS2, and then derive bounds for each one.
It's been quite a mathematical journey.
Using all sorts of tools and techniques, like changes of variables and inequalities.
Oh, yeah. Holders, Young's, trig identities, some pretty clever estimations, too.
To really get a handle on those complex integrals.
It's impressive stuff.
And remember, all of this was to understand the aspect ratio of the momentum support and how it changes over time.
Right, the main goal.
So how do they connect all these bounds they've derived to that aspect ratio?
Well, that's where it all comes together. They start by going back to the definition of the momentum support. It's the set of all momentum values where that particle density function, F, is non-zero at a given time, t.
Right. So it's like the region in momentum space where the particles are actually doing their thing.
Exactly. Now, they introduce a couple of new quantities, p1t, which is the supremum, or the least upper bound, of the absolute value of the first component of the momentum, p1, for all the momentum vectors within the momentum support at time t.
So it's like the maximum extent of the momentum support in that p1 direction at a given time.
Precisely. And then they define p2t in a similar way. But for the second component of the momentum, p2.
Okay, so p1t and p2t give us the maximum reach of the momentum support in each of those two momentum directions.
You got it. And now comes the connection to the aspect ratio. They define the aspect ratio, AT, as the ratio of p1t to p2t.
Ah, okay. So the aspect ratio is basically how much longer the momentum support is in the p1 direction compared to the p2 direction.
Exactly. And remember, they've already established a bound on pt, which is an upper bound for p1t.
Right.
So they can use that bound to control the aspect ratio as well.
Makes sense. If you have a limit on how far it can stretch in one direction, you automatically have a limit on the aspect ratio.
Now, to bring it all together, they go back to the definition of pt. And that inequality they derived, relating it to the integral of the electromagnetic force K over time.
The one that was like the culmination of all their work bounding KT, KS1, and KS2.
That's the one. They use this inequality along with the bounds they've established for K to derive a new inequality. That relates PP directly to P2T. And a few other terms involving time and constants.
So they're creating a tighter connection between PT and P2T.
Exactly. And this new inequality is the key to understanding the long-term behavior of the aspect ratio.
How so?
Well, the inequality shows that for sufficiently large times, PT is bounded by a function of time, P2T, and a logarithmic term.
Okay, so the maximum extent in the P1 direction is controlled by the maximum extent in the P2 direction. Time and a logarithmic factor.
Precisely. And since the aspect ratio is just the ratio of P1t to P2t, and PT is an upper bound for P1t, this result implies that the aspect ratio is also bounded for large times.
So even though the momentum support might stretch and change shape over time, its aspect ratio can't just grow indefinitely. There's a limit to how much more elongated it can become.
That's a great way to put it. And this finding has some pretty significant implications for understanding the long-term dynamics of these plasmas.
It feels like we've climbed a mathematical mountain.
It has been quite a climb.
We've seen how they started with this complex problem, broke it down into these smaller pieces, and then used all these amazing mathematical tools to overcome each challenge along the way. And they've arrived at a result that not only deepens our understanding of these plasmas, but also really showcases the power of math itself.
I completely agree. It's a testament to the beauty and depth of mathematics and its ability to help us understand the universe, even in realms as complex as plasma physics.
Well, thank you so much for guiding us through this intricate world of equations and insights. It's been a real pleasure.
The pleasure was all mine. And to our listeners, thank you for joining us on this deep dive. We hope you've enjoyed exploring the fascinating world of collisionless plasmas with us. Until next time, keep those minds curious and keep exploring the wonders of the universe.
All right, let's dive into the world of two-dimensional collisionless plasmas. These are systems where particles are so spread out that they rarely collide.
Yeah, they're governed mainly by those electromagnetic forces.
Really fascinating stuff. And today we're going to be focusing on how the shape of their momentum spread can actually tell us a lot about their long-term behavior.
Exactly. Think of it like this. Imagine a rectangle, right? And it's containing all the possible velocities of these particles.
Okay, yeah, I can picture that.
So what we're going to delve into is how the width of that rectangle relates to its height. It's a concept we call the aspect ratio.
So it's kind of like figuring out like the ideal screen shape, but for like a cosmic movie.
Precisely. And the movie here is how the plasma evolves over time, governed by a set of equations. They're known as the relativistic Vlasov-Maxwell system.
Okay, that's a mouthful. So RVM for short.
Yeah, RVM for short.
So this RVM system, it's like the rule book for how these plasmas change over time.
It is. It combines particle movement with the electric and magnetic fields that they actually generate themselves.
Right, okay. So pretty complex stuff.
It's notoriously complex, but understanding it can really unlock some deep insights into the behavior of plasmas.
And this has applications in a lot of different areas, right? Like astrophysics, fusion research.
Absolutely, and even technology development.
Wow. So one of the key challenges you said is proving global well-posedness.
Yeah.
Now, what exactly does that mean?
It essentially means ensuring that these equations that we're working with, these RVM equations, make sense and have a solution for all times.
So we need to make sure that this movie of the plasma's evolution doesn't just stop or become nonsensical.
Precisely. And in the case of 2D collisionless plasmas, we know that the answer is yes, but it really hinges on showing that the particle's momentum doesn't just grow infinitely large.
Okay, so momentum, it's basically a measure of a particle's mass and velocity combined.
Right, but with a relativistic twist because we're dealing with speeds approaching the speed of light.
Okay, so things get a little funky at those speeds.
A little funky.
Now, I understand that previous research had actually established bounds on momentum.
Yes.
But those bounds grew exponentially over time, which isn't really ideal if we want to understand the long-term behavior.
Absolutely, and that's where this deep dive comes in. Instead of just focusing on the maximum size of the momentum, we're looking at the aspect ratio of the momentum support, that rectangle that we were talking about earlier.
Right, representing all the possible particle velocity.
Is exactly.
Okay, so then the paper's setup introduces P2 of t as that maximum momentum in the vertical direction.
Right.
And we assume it grows over time. And then there's P of t.
That's right.
Which is the maximum momentum in the horizontal direction. And that's what we want to bound in relation to P2 of t.
Yes, exactly. And to make things a little more interesting, they also introduced this parameter, a W. It's a number between 0 and 1.
Okay.
And that's going to play a key role in controlling the aspect ratio. Think of it like a tuning knob. It adjusts the relationship between the horizontal and vertical momentum bounds.
Okay. I'm starting to see how this all fits together.
Yeah.
Now, equation 14 in the paper, that seems to be laying out like the core strategy here says to control P of t, we need to control the electromagnetic force acting on the particles represented by K.
Right. And the authors cleverly break down that force K into 3 different parts, KT, KS1, and KS2.
Okay. So each of these components captures a different aspect of that electromagnetic interaction.
That's right. And they require some pretty clever techniques to bound them.
So it's like we're trying to tame a 3-headed beast. We have to conquer each head separately to control the whole creature.
I like that analogy. So let's start with proposition 4 in the paper. This one tackles the KT bound. And this one's actually relatively straightforward. It builds upon the principle that the total mass of the plasma actually stays constant over time.
It makes sense. So it's like saying the total number of actors in our cosmic movie, it always stays the same, even though their individual movements might be changing.
Precisely. And this is formally expressed in Conservation Law 20. And when we combine this with the fact that the particle density function F is uniformly bounded, as stated in equation 12, it gives us a really powerful tool to start estimating KT.
So by using these fundamental constraints on mass and density, we can start to put a leash on that first head of the beast.
Exactly. And after a strategic change of variables and some careful integration, we get to this bound. KT of t, x, is less than or equal to a constant times t times P2 of t times log of P of t.
Okay.
And this bound reveals that KT grows linearly with time and proportionally to P2 of t, the maximum momentum in the vertical direction.
Okay. So far, KT seems to be behaving itself, growing at a reasonable pace. But I have a feeling things are about to get a little more complex with the remaining components.
You're right about that.
So what's the strategy for tackling KS1?
Well, that's where proposition 5 comes into play. And this is where we enter the world of light cones and some intriguing square roots of logarithms.
Right, light cones. Now, how do those play a role in bounding KS1?
Imagine a light cone like a ripple spreading out from, say, a pebble dropped in a pond.
Okay.
The math gets a little messy because we have to account for all the possible ripples from all the particles.
Right.
And that's where the division of the integration region into 3 parts based on that light cone comes in. It helps manage those pesky infinities that can pop up.
It's like strategically breaking up a complex puzzle.
Yes.
Into smaller, more manageable pieces, each representing a different section of the light cone.
Exactly. And as we piece together these integral fragments, we encounter those square roots of logarithms that I mentioned. They actually emerge from the geometry of the light cone itself.
It's fascinating how even in, this abstract world of math equations, the shape of something like a light cone can have a tangible impact on the calculations.
Absolutely. And after some skillful manipulation of these inequalities using tools like Holder's inequality and interpolation, we finally arrive at the bound for KS1.
Okay, so we've successfully tamed 2 of the 3 heads now, KT and KS1. But I'm guessing KS2 is where things get really tricky.
You're not wrong. Bounding KS2, this is where Proposition 6 takes center stage, and it employs some truly ingenious techniques.
So we're going to need all the tools in our mathematical arsenal to conquer this one.
We will. The authors really demonstrate incredible mathematical dexterity in this proposition. Yeah. And after navigating this maze of calculations, they emerge victorious with a bound for KS2 that depends on a fractional power of P of T. And this fractional dependence is actually crucial. It helps us close the estimates later on, ultimately leading to the proof of Theorem 1.
That's great. So by strategically breaking down the problem, carefully analyzing those light cone boundaries, and wielding some advanced math tools, we've now bounded KT, KS1, and KS2.
We have.
This is fantastic. So we've laid the groundwork for proving the main result of the paper. Yeah. Theorem 1, which establishes those critical bounds on the aspect ratio of the momentum support.
It's all coming together.
It is. Yeah. But before we dive into that, I think it's important to acknowledge the role of those conservation laws. You know, like equations 20 and 21. They've really been our guiding principles throughout this entire process.
Absolutely.
These conservation laws, they're like the guardians of this plasma universe.
That's a great way to put it.
Ensuring that the total mass and energy of the system remain constant, no matter how complex those calculations get.
Yeah, precisely. They are fundamental principles that not only guide our understanding of plasma behavior, but they also provide the essential tools that we need to construct rigorous mathematical proofs.
Right. Okay. So now with these bounds and conservation laws in hand, I think we're finally ready to tackle Theorem 1 and unravel the mysteries of the aspect ratio in two-dimensional collisionless plasmas.
Let's do it. All right, so we're ready for the final stage of our journey. We're going to dive into the proof of Theorem 1.
Okay, I'm ready. Sounds exciting.
Our goal here, remember, is to show that that horizontal momentum, P of t, can be bounded by a function of time, t, and that vertical momentum, P2 of t.
Right.
And this will basically reveal that relationship between the width and height of that momentum rectangle we've been talking about.
Right, that aspect ratio.
Exactly.
Okay, so where do we begin with this proof?
Well, the proof starts by revisiting equation 14. It reminds us that to control P of t, we need to effectively bound the total electromagnetic force. But thankfully, remember, we've already bounded those 3 components of it, KT, KS1, and KS2.
Right. It's like we conquered each of the 3 heads of the beast individually.
Exactly. Now we need to combine those victories to subdue the entire creature.
Sounds like a plan.
The first step here is combining those individual bounds.
Okay.
And to do this, the authors use a clever tool called Young's product inequality.
Young's product inequality.
Yeah. It's a powerful tool for controlling the product of multiple terms.
Right.
And after applying this inequality and working through all the resulting expressions, we get this really important estimate for K.
And that's represented by equation 59, right?
Yes, equation 59.
Okay, this feels like a turning point. Why is equation 59 so crucial?
Well, it provides us with a really concise expression for K, and it captures that dependence on T, on P2 of T and P of T. It's the key to unlocking the relationship that's outlined in Theorem 1.
It's like the missing piece to the puzzle. So now, armed with this powerful estimate for K, how do we actually proceed to bound that horizontal momentum, P of T?
Well, from here, it's pretty straightforward. We just plug our estimate for K from equation 59 back into equation 14. And this gives us a new inequality involving P of T, T, and P2 of T.
Okay.
Then we use Young's inequality again, carefully choosing our parameters, to get that desired bound for P of T. And with a touch of logarithmic finesse, we reach the conclusion. P of t is indeed bounded by that function of t and P2 of t, just like Theorem 1 states.
Amazing. It's remarkable how, after all that analysis, we've reached the summit and proven Theorem 1.
It really shows how powerful it can be to break down a complex problem, into smaller pieces, applying those clever techniques and using those fundamental principles.
Right, right. Okay, so help me wrap my head around this. What does this bound on P of t actually tell us about how those collisionless plasmas behaves?
Well, the key takeaway here is that the spread of momentum in one direction is intrinsically linked to the spread in the other direction. That bound on P of t, it demonstrates that the width of our momentum rectangle, representing the horizontal momentum, it can't grow infinitely without a corresponding growth in the height, which is represented by P2 of t.
So it's a delicate balance maintained by the electromagnetic forces.
Precisely. And this result has some pretty profound implications for a lot of fields, from astrophysics to fusion research and even technology development.
Oh, wow. So, it can help us understand the long-term behavior of plasmas in stars, galaxies, black hole jets.
That's incredible. And it goes beyond astrophysics, too. It impacts our efforts for clean energy through fusion, because in fusion reactors, controlling that hot ionized plasma is really crucial for getting sustained fusion reactions.
So these insights can help us design more efficient fusion reactors.
Exactly. We can optimize the magnetic field configurations and even the reactor designs themselves to make sure we're getting greater stability and efficiency.
That's remarkable.
It really is. It's like we're choreographing a cosmic ballet. The magnetic fields act as the stage, and the plasma particles are the dancers.
And by understanding the limitations on their movements, we can orchestrate that perfect performance.
Exactly.
This is really fascinating. It's amazing how a mathematical concept can have such a big impact, from fundamental physics research to space exploration and even material science.
Absolutely. It highlights just how interconnected all those scientific disciplines really are.
Yeah.
And it underscores why it's so important to pursue fundamental research, research that's driven by curiosity and a thirst for knowledge.
You're right. We often don't know where these explorations will lead, but they always seem to expand our understanding of the universe. I'm ready for Part 3, this deep dive.
Let's go.
Okay, so we've been through the math of Theorem 1 and seen how important this aspect ratio is. And we even touched on how it applies to things like astrophysics and fusion energy. But I'm curious, are there other areas where this research could lead to advancements?
Oh, definitely. The possibilities are pretty vast.
You mentioned technology development earlier.
Right, right. For example, think about particle accelerators.
Oh, okay.
Those giant machines that, smash particles together.
Right, to study the fundamental building blocks of the universe.
Exactly. And a lot of modern accelerators use plasmas to create the accelerating fields that push those particles to such high speeds.
Oh, so the plasma itself is part of the acceleration process.
It is, and by optimizing the shape and evolution of those plasmas, we could potentially achieve even higher energies and more efficient acceleration.
It's like fine-tuning the shape of a wave to carry a surfer further.
Exactly. And speaking of waves, another exciting area where this research could have a big impact is plasma propulsion systems for spacecraft.
Plasma propulsion. That sounds like something out of Star Trek.
It kind of is, but it's a real technology.
So how does it work?
Well, these systems use the momentum of ionized gas to generate thrust.
Okay.
And by understanding, those limitations on momentum spread that Theorem 1 describes, we could design more efficient and powerful propulsion systems. Imagine spacecraft traveling across vast distances using the power of plasma.
Wow. Yeah. That would revolutionize space exploration.
It would. And the applications don't stop there. This deeper understanding of plasma behavior could also be huge for material science.
Material science, okay.
Yeah, because plasmas are already used in a lot of different material processing techniques, things like etching, deposition, and surface modification.
Oh.
And by controlling the aspect ratio and other properties of the plasma, we might be able to create new materials with totally unique properties.
It's amazing how this seemingly abstract math concept can have such a broad reach.
It really is. It shows just how interconnected all these scientific disciplines are, and it reminds us how important it is to keep pursuing fundamental research.
Yeah, that research that's driven by pure curiosity.
Exactly, because we never know what we're going to find.
That's right. It's like we're constantly pushing the boundaries of our knowledge of the universe.
Well said.
Well, I have to say, this deep dive has been really enlightening. We've explored some complex math, uncovered the importance of this aspect ratio, and seen how it can impact all sorts of fields, from astrophysics to material science.
It's been a pleasure sharing this journey with you. I hope you found it as fascinating as I do.
I definitely have. It's a great reminder that even in those abstract math equations, there are hidden connections to the universe around us, just waiting to be discovered.
Exactly. And there are probably many more mysteries about plasmas still out there. Maybe future research will extend these results to 3 dimensions.
Now, that would be truly groundbreaking. Well, on that note, I think we'll wrap up this deep dive. Until next time, keep those minds curious and keep exploring the wonders of the scientific universe.
Until next time.